breakdown in a transistor. Breakdown in a transistor, right? Breakdown in a transistor. So first of all, what is a breakdown? So breakdown is nothing but the sudden increasing of current due to the high reverse voltage is called as what actually? Breakdown. I think already we discussed in our diode chapter, okay, the breakdown can happen in two ways. One is Zener breakdown, another one is avalanche breakdown. The Zener breakdown is occur in heavily doped PN junction due to what? High electric field. Avalanche breakdown is occur in lightly doped PN junction due to what actually? Collision of atoms, right? Now, what type of breakdown can occur in case of a transistor? Yeah, to know this actually, see the structure of a transistor actually. Here I am considering the PNP transistor. Right. See what I said actually. See, the Zener breakdown can occur in heavily doped PN junction and avalanche breakdown can occur in lightly doped PN junction. Now see this, it has two junctions, right? Emitter junction and collector junction. Now tell me, in these two junctions, which one is heavily doped? I think this one is heavily doped. That means at emitter junction, which breakdown can occur actually? Zener breakdown can occur, right? Similarly, at collector junction, which breakdown can occur actually? So I think it is a lightly doped. Which breakdown can occur? Avalanche breakdown occur. That means in a transistor, the both breakdown can be happened actually. That is Zener breakdown and avalanche breakdown. The Zener breakdown at emitter junction and avalanche breakdown at collector junction, right? Due to this, you know, breakdown voltage at collector junction is greater than breakdown voltage. BEV means breakdown voltage at emitter junction, because actually we have a relation between breakdown voltage and doping concentration. Actually, breakdown voltage is inversely proportional to what actually? Doping concentration. This is also I told in our chapter 2 diodes actually, right? Doping concentration. Doping concentration means if concentration is increases, means what about the breakdown voltage actually decreases. Here what I told, here avalanche breakdown is lightly doped. Lightly doped means doping concentration is decreased. That means breakdown voltage is increased. Similarly, the Zener breakdown is at a heavily doped PN junction. That means here the doping concentration is increased. That means the breakdown voltage is decreased. That means what is the conclusion actually? The breakdown voltage at collector junction is greater than breakdown voltage at emitter junction. Right? Yeah. Copy this one. First copy this figure. Yeah, copied now. Yeah, write down. Breakdown means, write down, breakdown means the sudden increasing of current. Breakdown means the sudden increasing of current due to the high reverse voltage, due to the high reverse voltage, due to the high reverse voltage. Next point. Next point. Breakdown can happen in two ways. Zener breakdown, in bracket, heavily doped PN junction, heavily doped p-n junction. Second point, avalanche breakdown in bracket lightly doped p-n junction. Lightly doped p-n junction. Yeah, bracket close. Completed. Yeah. Next one, in a transistor, Zener breakdown can occur at emitter junction, and avalanche breakdown can occur at collector junction. Right. Next point, that is breakdown voltage at collector junction. Breakdown voltage at collector junction is greater than breakdown voltage at emitter junction. Breakdown voltage at emitter junction. Yeah, copy this one. And 1 minute actually. This is represented with VCO and this is represented with VCB actually. 1 minute. Yeah, now you can copy. Oh, wait. I think this is VCBO. This is VCO. Yeah, sorry. This is VCBO. This is VCO. Right. I will tell you. Wait. Don't worry. Why this is VCBO and why that is VCO. Right. Completed? Yeah. Next one. Note. Yeah. Listen, all of you. Listen. See, the BJT gets damaged. Due to breakthrough or punch through. Already I told what is breakthrough or punch through or thermal runaway. Right? Thermal runaway actually. Right? Here, in case of BJT has two breakdown voltages actually. One is breakdown voltage BEV CBO and BEV CEO. Right. What is BEV CBO? BEV CBO is nothing but breakdown voltage at collector junction. Breakdown voltage at collector junction, right? When at collector junction when emitter is open. Emitter is opened. Similarly, what is BEV CEO actually? BEV CEO is nothing but breakdown voltage at emitter junction when base is opened. It has two breakdown voltages. Already I told na. One is breakdown voltage at collector junction, another one is breakdown voltage at emitter junction actually, right? Okay. Here, in case of BJT, if the VC is greater than or equal to breakdown voltage of VCEO, then what happens actually? The transistor, goes to breakdown actually. The transistor goes to breakdown. So we have a relation between breakdown voltage in two breakdown voltages actually. That is breakdown voltage at emitter junction is equal to breakdown voltage at collector junction nth root of 1 by beta, right? Where n is the constant. I think you know beta. What is beta actually? Beta is nothing but manufacturing parameter or common emitter current gain. This is the relation between the two breakdown voltages actually. Very important relation actually. Yeah. Write down. Write down the note actually. Write down the note. Write down. BJT get damaged. BJT gets damaged due to punch through or breakthrough, or thermal runaway, right? Next one, it has two breakdown voltages. Right? Yeah, write down this first one actually. Also write down this one. Write down these two voltages actually. Two breakdown voltages. These two. Yeah. Copied? Yeah, next one. See, if VCE greater than BVCEO, breakdown voltage at emitter junction. If VCE is greater than BEVCEO, then breakdown happened in a transistor. Right? Yeah. Now write down the relation between two breakdown voltages actually. BEVCEO equal to BEVCBO equal to into nth root of 1 by beta. Nth root of 1 by beta. Right. Yeah, copied? Yeah. Next, write in a question in classroom workbook, question number 3. In classroom workbook, question number 3. Right, write in a question. A transistor has beta equal to 100, comma, BEV at CBO equal to 40, means breakdown voltage at collector junction is 40 volts. And n equal to 5. N is constant. I already told you n is the constant. N equal to 5. Calculate breakdown voltage, means BEVCEO. Calculate BEVCEO. Breakdown voltage at emitter junction. Right. See, all of you read the question. What is the given data actually? They given beta equal to how much? 100, and breakdown voltage at collector junction 40, and n equal to 5. We want to calculate the breakdown voltage at emitter junction, right? May I know what is the relation between breakdown voltage at emitter junction and collector junction actually? That is BEVCEO is equal to CBO nth root of 1 by beta. What is the value of BV CBO? BV CBO is nothing but 40 into 5 at the root of 1 by 100. How much it is? This is 15.9 volts. Yeah, copy. Yeah, completed? Right. And next topic, configuration of BJT. Configuration of BJT. Configuration of BJT. Right. Yeah, so now all of you. So here first of all, what is configuration refers to actually? The configuration refers to how three terminals of the BJT can be connected is called as configuration of the BJT. Right? You know the BJT can be configured in three ways because it has three terminals, right? That's why it can be configured in three ways. See here all of you, first of all, I am drawing the BJT actually. It has three terminals, right? What are the three terminals actually? Emitter, collector and base, right? See, depends on the connection of terminals actually, the BJT can be configured in three ways actually, right? So one is common emitter. Common emitter, in short form I represented with CE, common emitter actually, right? And common collector and common base, C. Right? See, common emitter. Common emitter means emitter is common actually. If emitter is common, then input is given to what? If emitter is common actually, input is given to base, right? And what about output actually here? Output is given to what? Output is taken from, sorry, output is taken from collector. Next one, common collector. In case of common collector, actually collector is common. If collector is common, actually input is given to what actually? Base, but output is taken from emitter, right? Similarly, in case of common base. So here input is given to common base means base is common. Here input is given to emitter and output is taken from collector. This is what actually three configuration of the BJT, right? Yeah, right on. Right on. Configuration of BJT refers to, right on, configuration of the BJT refers to how three terminals of the BJT can be connected. How three terminals of the BJT can be connected. Three terminals of the BJT can be connected. Right? Next point. The BJT can be configured in three ways. BJT can be configured in three ways. Right? Yeah. Write down these three configurations. Right, completed. Yeah, the first heading, common base configuration. The first configuration, common base configuration. Copy parallelly. See, in common base configuration, the base is common, right? Base is common means base is connected to ground. Yeah. This is the common base configuration actually. Yeah, soon all of you copy it, right? Yeah, in common base configuration, actually the base is connected to ground, right? Input is given to emitter and output is taken from the collector, right? Now, here we want to observe the input and output characteristics actually, right? In common base configuration. Now, first I am going for input characteristics. Input characteristics, right? So the input characteristics are drawn between, in case of common base configuration, input characteristics are drawn between IE versus VEB, right? By keeping which one is constant actually? By keeping VCB is constant. VCB is constant, right? Now see here, what is this IE actually? This IE is nothing but current through this emitter junction. Am I correct or not? This IE is nothing but current through this emitter junction, and this VEB is nothing but voltage across the emitter junction actually. See here there is a junction actually. Here there is a junction. I already told you what is BJT. Actually, BJT is nothing but back-to-back connecting of the two diodes actually, right? This IE is nothing but current through this emitter junction. VEB is nothing but voltage across the emitter junction. That means the input characteristics are resembles the diode junction characteristics. Diode junction characteristics, right? See here, for small values of VEB, actually, what about the emitter current? Actually, the emitter current is negligible. For small values of VEB, emitter current is negligible, right? See, VEB is, if VEB is greater than the cutting voltage, that may be a silicon 0.7 or 0.3 actually. If it is greater than the cutting voltage, what happens actually? The current suddenly increases. Here I think this point is the cutting voltage actually. Here this point is the cutting voltage. This is what actually the VCB1 and VCB2. VCB1 and VCB2, right? That means see all of you here this emitter current is depends on what actually? This emitter current is depends on VCB due to what actually? Early effect, right? See, this emitter current depends on what actually? Due to early effect actually, right? How it will depends on early effect actually? See all of you, how it will depends due to early effect? If VCB is increased, Already in my previous lecture, I already told, if the VCB is increased, VCB increases means voltage at collector junction is increased. Following or not, all of you? If VCB is increased, what happened to the effective base width? The effective base width is decreases. Effective base width is nothing but what actually here? Effective base width is nothing but delta X, right? If effective base width is decreases means what about the concentration gradient actually? dP by dx actually? dP by dx is increases. If dP by dx is increases means actually what about the IP actually? IP is increases. If IP is increases means what about the emitter current actually? Increases. See here, this VCB depends on what actually? Emitter current. This VCB depends on what actually? Emitter current. See, for a given value of VEB, this emitter current is increases with this VCB. Okay, for a given value of VEB, this emitter current is increases with VCB. Okay, see, if the VCB is increases, if this VCB is increases actually, these input characteristics are shifted left side like this, shifted left side, right? Yeah, copy the input characteristics first heading, input characteristics, first heading, input characteristics. Write down it is a plot of IE versus VEB. It is a plot of IE versus VEB. Right. Next point, IE versus VEB. By keeping continue. By keeping VCB is constant. Right. Next one. IE is the current through the emitter junction. IE is the current through the emitter junction. VEB is the voltage across the emitter junction. That means the junction, the input characteristics are resembles the diode junction characteristics. The diode junction characteristics. Right. Next point. For small values of VEB, IE is 0. For small values of VEB, IE is 0. Next, if VEB greater than cutting voltage, means if VEB crosses the cutting voltage, the emitter current suddenly increases. Right. Next point. Emitter current depends on VCB. Due to early effect. Right. Yeah, copy this one. How it will depends on VCB. Yeah, completed. Next one. For a given value of VEB, next one, for a given value of VEB, for a given value of VEB, IE is increases with VCB. IE is increases with VCB. IE is increases with VCB. Next one, if VCB is increases, next point, if the VCB is increases, then the input characteristics are shifted left side. Input characteristics are shifted towards left side. Input characteristics are shifted towards left side if the VCB is increased. Right. This is about input characteristics of common base configuration. Right. Yeah. The next one, output characteristics. Just right. Yeah, I think output characteristics. Right. So no. So here output characteristics are drawn between IC versus VCB by keeping which one is constant actually? Emitter current is constant. Emitter current is constant. Right? Now see here, if emitter current equal to 0 first. If emitter current equal to 0. If emitter current equal to 0, then what happen actually? Okay, the output characteristics are resembles the junction characteristics. Means junction diode characteristics. See how junction diode characteristics actually see all of you. Right. Yeah. Actually, why the characteristics are like this? You know what is this collector current actually? You know this collector current is a sum of two currents actually. This collector current is the sum of the two currents actually. One is the current is due to carriers which are coming from the emitter. Actually, this collector current is okay due to two types of currents actually, summing of two currents, superposition of the two currents actually. Okay, one is the current due to carriers which are coming from the emitter, and the current due to okay applied voltage, that is VCB. Applied voltage, that is VCB, right? Here, when emitter current equal to 0, then okay the output characteristics are exactly resembles the diode junction characteristics like this. That means the forward characteristics are drawn in the third coordinate and reverse characteristics are drawn in the first coordinate. Right? If emitter current is greater than 0, what happen actually? If emitter current is greater than 0, the characteristics are shifted upwards like this. Shifted upwards like this. Shifted upwards. This is IE equal to 0. This is IE1. This is IE2. And this is IE3. Right? This is the output characteristics of common base configuration actually. Right? Yeah, copy up to this. Write down output characteristics. It is a plot of IC versus VCB by keeping emitter is constant. Right. Next point. Collector current is a sum of two currents. Collector current is a sum of two currents. Sum of two currents. One is current due to carriers. One is current due to carriers which are coming from the emitter. Which are coming from the emitter. Second one, current due to applied voltage. Current due to applied voltage. Applied voltage, that is VCB. Applied voltage VCB. Yeah, next point. If IE equal to 0, if IE equal to 0, then if IE equal to 0, then the output characteristics are resembles the junction diode characteristics. Junction diode characteristics. That is, forward characteristics are drawn in third coordinate. Forward characteristics are drawn in third coordinate and reverse characteristics are drawn in the first coordinate. Reverse characteristics are drawn in the first coordinate. Right. Next point. If emitter current is greater than 0, if emitter current is greater than 0, then the output characteristics are shifted upwards. Output characteristics are shifted upwards. Shifted upwards. Right? Yeah. Copied? Yeah. Next, soon all of you. See, based on this output characteristics actually, so right, the BJT operated in three modes actually, right? Three regions. One is cutoff region, and saturation region, and active region. Right. So first, cutoff region actually. The first we start with cutoff region actually. Cutoff region. See, what is cutoff region actually? Cutoff region is nothing but, okay, the region in which cutoff region is nothing but the region in which emitter current is 0. Emitter current equal to 0 and right of VCB. Right of VCB. See, emitter current equal to 0, right of VCB means, I think, which portion? I think this portion. I think this is what actually cutoff region. Cutoff region actually. Right? See here, if emitter current equal to 0, then what about the emitter junction actually? The emitter junction is operated in which bias actually? Reverse bias. See, if emitter current equal to 0 means no current is flowing. No current is flowing means then it is in which bias? Reverse bias actually. Similarly actually, right of the VCB. Right of the VCB means, I think VCB is greater than 0, right? If the VCB is greater than 0, I think the collector junction also what actually? Reverse bias, right? See, VCB greater than 0 means, I think this cathode is greater than anode, right? That means it is in reverse bias actually. If emitter junction is reverse, collector junction is reverse, that means what is the region actually? Cutoff region. Right? Right out up to this. Right out. Based on output characteristics, Based on output characteristics, BJT is operated in three regions. The first one cutoff region. Second one saturation region. And third one active region. Yeah, the first one cutoff region. Write down the region in which IE0 and right of VCB. The region in which IE0 right of VCB. Right. Yeah. Copy this one. Yeah. Next one. Saturation region. See, what is saturation region actually? Saturation region is nothing but the region in which, okay, IE is greater than 0 and left of VCB. See, IE greater than 0, left of the VCB means I think this portion, right? Left of the VCB means I think this portion, right? This is the which region? Saturation region actually. This portion is saturation region actually. See all of you. See here, if IE greater than 0, emitter current is greater than 0 means I think emitter current means current through the emitter junction, right? See, it is greater than 0 means current is passing. Means I think this junction is in which bias actually? Forward bias. Right. The next one, okay, left of the VCB. Means I think VCB is less than 0. If VCB greater than 0, collector junction is reverse. If the VCB is less than 0, the collector junction is in forward. If both junctions are forward means I think it is in which region? Saturation region. And one more point actually, in case of saturation region, okay, the collector current depends on actually what actually? The collector current will depends on emitter current as well as VCB. It depends on both actually, right? Yeah, copy. Write down saturation region. The region in which IE greater than 0 and left of the VCB. Right, left of the VCB. Yeah. Write down these conditions. Copied? Yeah, write down. In saturation region, next write down a point. In saturation region, the collector current depends on, both IC and VCB. Right. And the last one, active region. Yeah. See, what is active region actually? Active region is nothing but the region in which, okay, emitter current is greater than 0 and also left of the VCB. Left of the VCB. See, emitter current is greater than 0. Left of the VCB means I think this portion actually, right? This region is called as what actually? Active region. Right? See, if emitter current is greater than 0, right? If emitter current is greater than 0 means, I think what is emitter junction? Emitter junction is in which bias actually? Forward bias, because greater than 0 means current is passing, right? Current is passing means it is in forward. And similarly, left of the VCB means I think VCB is, okay, greater than 0, right? If the VCB is greater than 0, then what about the collector junction actually? Reverse bias. Emitter junction is in forward, collector junction is in reverse. That means that means it is operated in which region? Active region, right? And one more point actually, in case of active region, this collector current will depends on what actually? This collector current will depends on emitter current and independent on VCB. See here, whatever the value of VCB, what about the IC actually constant, but it will depends on what actually? IE, right? Because we have a relation actually, that is IC equal to minus alpha into IE plus IC naught. In common base configuration, I think this is the collector current equation in active region. In active region, this is the collector current. See here, this collector current will depends on what actually? Emitter current, but independent on what actually? VCB. Right? Yeah, right on. Right on. The reason in which IE greater than 0, IE greater than 0 and left of the VCB, left of the VCB, right? Write down these conditions, two conditions. Write down these two conditions. Right. Write down. In active region, the collector current depends on IE. The collector current depends on IE and independent on VCB. Independent on VCB. Because write down IC equal to minus alpha into IE plus IC naught. I think you know what is alpha, common base current again. IC naught is nothing but, I think we know, already we derived this equation. IC naught is nothing but reverse saturation current or leakage current, right? This is about common base configuration and its input characteristics and output characteristics, right? Yeah, thank you. To be continued in next lecture.